Coupled oscillators. Consider a system of coupled oscillators with general coordinates q1, q2, and so forth, qn, arranged in a column. We will give name to this column q, so that q equals 0. Note, this is a column, means equilibrium. Let's find the equation of motion of this system with coupled oscillators. We start out with writing the kinetic energy. We know that kinetic energy for Cartesian coordinates would be written simply as mass that corresponds to each Cartesian coordinate times velocity squared. That is true for Cartesian coordinates. How will the kinetic energy look for generalized coordinates? In other words, when coordinates that describe the position of coupled oscillators are no longer Cartesian. What we have in this case is that Cartesian coordinates can be expressed in terms of generalized coordinates. Therefore, using chain rule, we can write the velocity of Cartesian coordinate r sub I to be given by sum with index j, partial derivative of r sub I with respect to generalized coordinate q sub j times generalized velocity q sub j dot. Next, if we are to write velocity squared, it will simply be given by the product of these two sums, which we can write as a sum along j index of partial derivative of r sub I with respect to q sub j times generalized velocity q sub j times another sum, let's give it subscript k, partial derivative of r sub I with respect to q sub k times generalized velocity q sub k dot. Then we can rewrite kinetic energy in terms of the sum above, half of mass Ri dot squared, given by a triple sum, a double sum with respect to j and k, and another sum with respect to index I, m sub I, partial derivative of r sub I with respect to q sub j, times partial derivative of r sub I with respect to q sub k, times q sub j dot and q sub k dot. Note that this coefficient here we can call a sub jk. Therefore, we can write that kinetic energy is given by half of double sum along coefficients j and k of a sub jk times generalized velocity q sub j dot and generalized velocity q sub k dot. Note that the coefficients a, j, k are symmetric. If we change the order of j and k, we get the same thing. And also note that generally it's a function of the column q. Next, we want to find potential energy. Potential energy will depend on the column q, and we will use Taylor expansion u of 0, where both q and 0 here are columns, plus sum of partial derivative of u with respect to q sub I evaluated at q equals 0 times q sub I plus half of double sum j and k partial mixed derivative of u with respect to q sub j and q sub k evaluated at q equals 0 and multiplied by q sub j and q sub k plus higher order terms. First, we note that since we're expanding around the equilibrium position, the first partial derivative will vanish. The coefficients in front of the second sum we can give names of k sub jk. Again, we know that k sub jk is symmetric. In other words, k sub jk is equal to k sub kj. Now we are ready to produce the equation of motion, which, as we know, is given by partial derivative of Lagrangian with respect to coordinate q sub I. On the left-hand side and on the right-hand side, full-time derivative of partial derivative of Lagrangian with respect to generalized velocity q sub I dot, where I will have values from 1 to n. First, let's work on the left-hand side. The left-hand side will be given by partial derivative of u with respect to q sub I, or it will be given by partial derivative with respect to q sub I of the sum, double sum jk, k sub jk times q sub j times q sub k. Well, we note that this sum given by q sub I times coefficient k sub I1 times q1 plus all the way to k I n times q sub n. And then another term will be given by q sub I times the opposite order of the indices, k sub 1 I times q1 plus all the way k n I times q sub n. When we differentiate it and use the fact that these terms are equal, because K matrix is symmetric, we obtain that this partial derivative is equal to a sum of K sub ij times Q sub j. Let's work on the right-hand side now. The right-hand side is given by full time derivative of kinetic energy with respect to velocity q sub I dot, which by direct analogy we write immediately to be given by sum of j of matrix I sub ij evaluated at q equals 0 times q sub j double dot. We will call this matrix M I sub j. Thus we write that this partial derivative will be given by the sum of M sub ij times q sub j summed over indices j. Equating these two, we get our equations of motion. We get that the sum of M ij times q sub j double dot is equal to minus the sum of j of k ij times q sub j for I from 1 to n. This equation of motion is best written in the matrix form. Matrix M, which consists of coefficients Mij times Q double dot, where Q is n column, equal to minus matrix K, which is given by coefficients K sub ij, times the column Q. Thus, M and K are n by n symmetric matrices. We can readily identify M as mass matrix and K as spring constant matrix, and Q, generalized coordinates, is an n-column vector.